thing in mathematics is when you do pure mathematics or rigorous mathematics, once you, or axiomatic mathematics, you always play within the rules of the game, namely the axioms. You are never allowed to violate this. If you are violating it, then you are playing a different game. It's like chess. So that's the thing that you have to prove. And having proved that, a lot of properties that you are used to follow from that, which can be proved. I mean, each one of them requires a proof. I am not going to do it. If I were to do it, I may have to take something like 40 or 50 lectures to complete the whole task. But let us look at that. What all things you get? You would have proved that x plus y plus z equal to x plus y plus z for every x, y, z belonging to n. That means it is associative. What does it mean? Let us read it. You take x, add to it the sum of y and z. That's the meaning of this bracket. This is equal to the sum of x with y added to z. It is immaterial which way you add it, therefore you can eventually discard this bracket. So this is what is called associativity. So you can prove all this. You have to prove within the axioms. Second one that you prove is that x plus y equal to y plus x. This is commutative. That means you take first x and then add y to it, or take first y and then add x to it, you get the same thing. So this is what commutativity, and you know that there are systems where commutativity is not valid. That's why you make it one of this. So what we do is the following, and few things that we note is that y is not equal to y plus x. So when you add some natural number to y, you get a different number. Okay? You never get the same number. The fourth one. If y is not equal to z, then this implies all these are to be proved and has to play the game within these structures, and I'll tell you which book you can look into. And the fifth one is very interesting and very useful. You see that given x, y belonging to n, either x equal to y or there exists u such that x equal to y plus u, or there exists v belonging to n such that y equal to x plus. Okay, let us see what it is. Let us work with an example, then it will be clear. So given x and y, let us take 2 and 5. X I take as 2, Y I take as 5. So first of all, 2 is not equal to 5. That's clear. Then what are the other possibilities? Or there exists X is 2, Y is 5. Of course, there does not exist any U such that X is equal to 5 plus U. Okay? But you see that 5 is equal to 2 plus 3. That means there exists a V such that Y is equal to X plus V. Only one of the three will be true, not all the three or all two of them simultaneously. Okay, this is one of the properties of the number system. Incidentally, don't get confused. You might ask, okay, if you have X and Y, X equal to 2, Y equal to 5, why not write this as, why not take this as minus 3? We don't have minus 3 yet. Okay. In n, there is nothing called minus 3. Okay, we have only 3. Right? So you are confined yourself to the set n and to nothing else. We don't have the other parts of the number system readily available at the moment. So you forget that at the moment. Okay. This is a very important thing. What does it say? You are asking, you have a question here. The question is this: given X, Y belonging to n, you are asking, does there exist a solution of the equation you don't know U, you are given X and Y. Okay? Does there exist a solution? What you know right now is that in n, given X and Y arbitrarily, sometimes there is a solution. Not always. Okay? Right? Right? For instance, if both X and Y are the same, then there is no solution at all, because we don't have 0 yet. If you take X equal to 2, Y equal to, or X equal to 2, Y equal to 5, then there is a solution. If you take X equal to 5 and Y equal to 2, then there is no solution at all, because you don't have negatives yet. Okay? So this is the crucial equation that's going to play. Don't just keep it in your mind. We'll come back to it quite about that. So what this criteria 5 says is that this equation has a solution in certain circumstances and not always. That's what we say. Okay, that gives us a new structure. So we introduce the next structure. So this is the addition. The next structure is what you call order structure. Order structure. What it says is that if you have X and Y, then there may exist a U or may not exist a U. That means this equation may have a solution and may not have a solution. Okay? Suppose for given x comma y, this equation has a solution. Then we say x is less than, okay. For instance, 2 is less than 5, but 5 is not less than 2. Okay? So we write less than, we introduce the notion of less than, this that gives an order structure. So given two elements, either x is less than y or y is less than x, but not both. So there is a well defined order structure on the line. Okay? If on the other hand, suppose no solution, then we have y less than x or x greater than y. This is the same thing. This is the same thing. This is synonymous. Y less than x is the same as x greater than. Okay. Then of course, let me not, if I were to list out the properties etc., then I won't have much time. Now what you have on N, you have two structures, namely addition okay. Now we also introduce a new notation, namely less than or equal to. Less than or equal to means what? Given x and y, either x is less than y or x is equal to y. One of the two possibilities are there. You fuse them together and call it less than or equal to. Okay. For instance, 5 is equal to 5, 5 is less than 6. Okay, so only one of the things are valid. So x less than or equal to y, if and only x less than y or x equal to y. This is also we use. And there is the analogous thing. If x is less than or equal to y, implies if and only if y is greater than or equal to x. So, x is less than y implies y is greater than x. Y greater than x implies x is less than y. Now, the important thing is that if they are not obvious, all of them have a needed. Okay. So you have so many properties associated with it. I do not want to list them because now you see this is important. There are two things. One, already there is an addition with respect to which certain properties are satisfied. Now you have an order structure. How these two interact together? This is a question that you have to mention. Now this is true for any mathematical system. If you have a mathematical system with the two operations, star and say two operations are there on the same set, then you have to say how these two, the elements here are, for instance, x star y will be defined, I will call this some operation y is defined. Now how these interact, these two operations interact together. For example, look at here. Suppose you have x less than or equal to y. Now what happens? X plus u is less than or equal to y plus u. Okay, addition is there, this is also there. So also x is less than or equal to y, x1 is less than or equal to y1, then you have x plus x1 less than or equal to y plus y1. All these things can be proved within the axioms and the definition of the order structure. Okay? And specifically a few things that are important here is x is greater than or equal to 1. 1. It is always greater than or equal to 1. Or 1 is the least element. Okay? And x is y is less than y plus 1. Okay, y is not equal to y plus 1, y is less than y plus 1. Okay, so this property is right. Therefore, one of the things that you can say is that this is important. If A is a subset of n, then there exists A belonging to A such that A is less than or equal to x for every x belonging to. What does it say? It says that there is a least element in any subset of n. Okay. There is a smallest element in any subset of n. This is true. But can you say there is a largest element in every subset of n? It's not possible. Also, you take just the even natural numbers. Does it have a greatest element? No. So this is the statement that we can make about n. Every subset in n has a least element. Okay. That is something about the order. Now come to the next one. The next structure is, so order has come out of this particular equation, namely x plus u equal to y, whether it has a solution or not. This is the question. It is from there that the order structure has evolved. Now we introduce multiplication. How does multiplication come? Okay. What is multiplication? Multiplication is the repeated addition. No? What do I mean by that? You take 2 into 5 is essentially add 5 times 2. That means 2 plus 2 plus 2 plus 2 plus 2. That is 5 times you have added 2. This is how you have defined it. Now let us see whether we get it. So we give a definition. The first thing that you observe is that we postulate x into 1 is equal to x. And then we write x into y prime is defined as x plus, x y plus x. This is the definition. Okay. x prime equal to x plus 1. This is one of the things that you can prove. Okay. Let us see whether this gives you the multiplication. Suppose you want to multiply 2 into 3. How do you write this? 2 into 3 is 2 into 2 prime. But what is 2 into 2 prime? This is equal to 2 into 2 plus 2. Okay? Yeah, I have used this. And let me again use this. So 2 into 2 is 2 into 1 prime plus 2. What is this? This is equal to 2 into 1 prime is, so this by definition, this is actually 2 into 1 plus 1 plus 2. But 2 into 1 is 2, so this is 2 plus 2 plus 2. Okay? But it is a repeated addition. 3 times you add 2 to itself. Okay? So that's what you get. So this is the school definition that you are familiar with, which has been put in this form. So this is true for every x, y belonging to. So you have now addition, order relation and multiplication. Therefore one has to talk about the interplay between them. Okay. So you have x into y into, say, equal to x into y z. This is what you call associativity. This is commutativity. X into 1 equal to x. That is of course a repetition of the first property. Okay.